We've talked about them a few times before, but let's formally introduce them here. So today we're going to talk about, in this lesson, capacitors, specifically capacitors and material between capacitor plates, which is called a dielectric. So first, let's introduce capacitor. A capacitor is just a device that's used to store electric charge, and therefore, since it stores electric charge, it actually stores energy. So capacitor you can think of is similar to a battery in that it can store energy. But unlike a battery, it stores energy because of a charge difference between the plates, whereas a battery stores energy in the chemical energy inside the battery. It is comprised of basically two conductors, so two conducting pieces of material, two pieces of copper, two pieces of aluminum, whatever, as long as they're conductors, and they have to be separated by an insulator. So charge cannot go from one conductor to the other. So the simplest version of this is called a parallel plate capacitor. Now, a parallel plate capacitor is just a system composed of two parallel plates, so two plates that are basically parallel surfaces separated by some distance. And I have an example here. So we have a conducting plate, big metal conducting plate, and this metal conducting plate, you have two. Place it onto this bench here. I can separate it by some distance. I can change that distance. So you have some distance here, but see how the conducting plates aren't in contact with one another. So I can attach on one end of the plate a wire, part of a circuit. On the other plate, I can attach a wire or circuit. So I can charge one plate, dump positive charge on one plate, and on the other plate, negative charge will appear. The charge wants to cross. It wants to jump the gap, but can't because there's an insulating material between it or a vacuum. Air is a pretty good insulator, right? You walk past an electrical outlet, lightning doesn't jump from the outlet to strike you. But air doesn't work perfectly well, as all of us have experienced. If you've ever rubbed your shoes on a carpet and then went to touch a door handle, you can get a spark, right? Static electricity can build up, and electricity can actually jump through air, ionizing the air. That's what lightning is. So much charge builds up between the earth and the clouds that potential is so ridiculously great that it actually ionizes the air and causes charge to flow. In a capacitor, ideally, you don't want charge to flow between these two capacitor plates. If I set up such a large potential between these two plates that lightning starts to jump between these two plates, I've basically ruined the capacitor. So parallel plate capacitor is the simplest version, and we'll come back to this in a moment. The ability for a capacitor to store charge, because that's the function of a capacitor. It stores charge. The ability of it to store charge is called the capacitance. Think of it like a swimming pool has the ability to store water. How much water can the swimming pool store? Well, that depends on how big the swimming pool is. A capacitor you can think of as a charge storage device. How much charge can it hold? Well, it depends on two things. It depends on what the potential difference is between the two plates. If there is no potential difference between the two plates, no charge is stored on the capacitor. And how big the capacitor is, how efficient it is at storing charge. So the equation we're going to be talking about is the charge stored on the capacitor, charge Q, is equal to the capacitance of that capacitor. And in a moment, we'll talk about how to calculate that for the simple parallel plate capacitor, times the potential difference between the two plates. Is there a 9-volt difference between the two plates, 12 volts, 1,000 volts? What potential difference did you put between those two plates? Zero potential difference means zero charge, regardless of the capacitance, right? If you don't put any water in a swimming pool, the swimming pool holds no water, regardless of how big the swimming pool is. Now, you can see that this is a linear relationship. The amount of charge shown here on the y-axis increases as the potential shown here on the x-axis increases. How fast the charge increases with potential depends on the slope of the line. The slope of the line is the capacitance of a capacitor, right? Think of this as y is equal to mx plus b, right? Our old favorite linear algebra or line equation in algebra, not linear algebra. The line equation in algebra, y equals mx plus b, m is the slope, b is the intercept. Well, the intercept here is 0, so there is no b term. You can see, right, there's nothing, no addition term here. X on the x-axis is the potential. The y-axis is the charge. The slope is the capacitance. So a high capacitance capacitor would have a very large slope. A low capacitance capacitor would have a smaller slope. But they'd all be lines. So again, Q here is the charge stored by the capacitor. Now we have two capacitor plates, remember. One capacitor plate will store a charge of plus Q. The other capacitor plate will store a charge of minus Q. So the net charge on this capacitor is actually 0. And that's true for all capacitors. The net charge is always 0. But this is not net charge. This is the amount of charge on one of the plates. So if you have here, you figure out Q, let's say your capacitor is storing 2 coulombs of charge. That means one plate has plus 2 coulombs of charge, and the other plate has minus 2 coulombs of charge. That does not mean there's 4 coulombs of charge here. That does not mean there's 0 coulombs of charge, although the net is 0. This Q tells you the magnitude of the charge on each plate. Now, Q is units of coulombs, SI units of coulombs is a charge. Potential has SI units of volts. Capacitance has SI units as well. The SI unit for capacitance is called the farad. So 1 coulomb is equal to 1 farad times 1 volt. Or solving this for capacitance, right? Capacitance is equal to charge over potential. That's the slope of the line. So 1 farad is 1 coulomb per volt. So let's look at how do we determine what the capacitance of a capacitor is.